standing on a sort of design lab. This is where they controlled the architecture of the pyramid.
The plan of the pyramid is the pyramid itself, because if you really want to keep something that accurate, the way to do is to make your plan at the same size as the finished thing.
For over a century, the Great Pyramid of Giza has been explained as the result of ancient Egyptian engineering using simple tools and massive labor. But a new analysis by Grok AI suggests something unusual. When archaeological, geological, and engineering data are examined together, patterns begin to emerge that don't fully align with the traditional explanation. From extreme precision to unexpected mathematical relationships and tool marks that defy expectations, the findings raise a question that has never been fully resolved. How was the Great Pyramid really built? The conventional story of the pyramid. The widely accepted explanation places the construction of the Great Pyramid of Giza around 2560 BCE, during the reign of Pharaoh Khufu of Egypt's 4th dynasty. Within mainstream archaeology, this monument is considered one of the greatest achievements of the ancient world, built not through mystery or lost technology, but through highly organized human effort, administrative planning, and long-term logistical coordination. According to this consensus, the pyramid was constructed by a large and structured workforce composed primarily of skilled laborers and seasonal workers. These workers were likely supported by farmers who contributed during the Nile's annual flooding periods, when agricultural fields were submerged and farming activities were temporarily paused. This seasonal labor model is often used to explain how ancient Egypt could mobilize such a massive workforce without disrupting its food production systems. Within this framework, the construction process relied on relatively simple but effective tools and techniques available at the time. Copper chisels were used to shape and cut softer limestone blocks, while stone hammers helped refine and adjust the stone surfaces. Wooden sledges were employed to transport massive blocks across the desert terrain, often assisted by teams of workers pulling the sledges over lubricated surfaces such as wet sand to reduce friction. To raise the stones to higher levels of the structure, large ramp systems are believed to have been used. These ramps may have taken different forms depending on the construction phase, including straight ramps extending outward, spiral ramps wrapping around the structure, or zigzagging systems that adjusted direction as the pyramid rose.
Believe that some kind of ramp was used to raise the stone blocks. The type of ramp remains a mystery.
These theoretical ramp models are central to explaining how multi-ton limestone blocks could have been positioned layer by layer as the pyramid gradually took shape. Supporting this reconstruction is a significant body of archaeological evidence. Excavations near the Giza Plateau have uncovered worker villages, suggesting the presence of a sustained and organized labor force living near the construction site. These settlements include housing structures, bakeries, and communal facilities, all indicating long-term habitation and large-scale workforce management. In addition, ancient administrative records and inscriptions provide insight into logistical operations such as food distribution, workforce organization, and material transport. These documents suggest that the Egyptian state possessed a highly structured bureaucratic system capable of coordinating complex projects over extended periods. Quarry sites located both locally and at distant locations also show clear signs of large-scale stone extraction and transport, consistent with pyramid construction activities. On paper, this explanation forms a coherent and internally consistent system. It demonstrates how a pre-industrial civilization, using available tools, environmental advantages, and strong administrative control, could theoretically organize tens of thousands of workers and complete a monumental architectural project over an estimated 20-year period. Within this model, the pyramid becomes not a mystery of lost technology, but a testament to human coordination, discipline, and persistence. However, this reconstruction is based on a combination of physical evidence and informed assumptions about efficiency, construction methods, and labor capabilities. While each component of the model is supported by archaeological findings, The complete step-by-step process of construction has never been directly observed and must be inferred from incomplete data. This means that while the framework is persuasive, it is not fully reconstructible in real-world experimental terms from start to finish. Certain aspects, such as exact ramp configurations, precise transportation methods, and real-time construction logistics, remain subjects of ongoing debate and modeling rather than definitive proof. And when the pyramid itself is examined more closely, particularly its geometric precision, structural consistency, and alignment with astronomical features, additional characteristics begin to emerge that are difficult to replicate even with modern engineering methods. These observations do not immediately contradict the conventional model, but they do introduce complexities that continue to invite further investigation and discussion. Engineering precision that challenges expectations. One of the most striking features of the Great Pyramid of Giza is its extraordinary geometric precision. The base of the structure is leveled with an accuracy of just a few centimeters across a span exceeding 200 meters on each side. This results in an almost perfectly flat foundation, a feat that requires extremely controlled surveying conditions. Even with modern equipment such as laser leveling systems and digital measurement tools, achieving this level of uniformity over such a large area would still demand careful calibration, repeated verification, and ideal working conditions. Even more remarkable is the pyramid's alignment. Its sides are oriented almost exactly to true north, with only a very small and measurable margin of error. Achieving this degree of directional accuracy would require either highly precise astronomical observation, tracking celestial bodies over time, or advanced directional tools capable of maintaining consistent reference points. In modern engineering, such alignment is typically achieved using GPS systems, satellite data, or advanced geodetic instruments, none of which were available in ancient Egypt. Modern construction standards for large-scale structures generally allow for small deviations due to material inconsistencies, shifting ground conditions, temperature changes, and human limitations. Even with advanced technology, perfect uniformity is nearly impossible to maintain across every stage of construction. The Great Pyramid, however, appears to consistently exceed these expected tolerances rather than fall within them, maintaining a level of precision that stands out even by today's standards. Then there is the issue of construction speed and logistical execution. Based on accepted timelines, estimates suggest that hundreds of multi-ton limestone blocks would need to be transported, lifted, and placed every single day to complete the structure within approximately 20 years. This implies not only a massive and well-organized workforce, but also a highly efficient system capable of continuous operation without significant delays, bottlenecks, or structural errors accumulating over time. Individually, each of these factors, precision leveling, near-perfect alignment, and rapid large-scale construction, can be explained through theory and reconstruction models. However, when considered together as part of a single project, they begin to form a more complex picture. It raises a fundamental question.
It's almost what you don't see here that is even more impressive than the pyramids themselves.
Does the Great Pyramid represent the gradual refinement of a developing construction system, or the application of a fully formed and highly advanced method from the very beginning of its creation? Mathematical patterns embedded in stone. When Grok AI analyzed the full set of dimensional data from the Great Pyramid, it identified a series of mathematical relationships that appear to extend beyond what would be required for basic structural design. One of the most widely discussed findings involves the relationship between the pyramid's height and its perimeter. When expressed within certain measurement interpretations, this ratio closely approximates the value of pi, a fundamental constant associated with circles and geometry. In addition to this, other proportional relationships within the structure appear to correspond with the golden ratio, a mathematical constant often associated with natural growth patterns, biological structures, Art and architecture. The golden ratio was formally defined much later in human history, yet similar proportional relationships seem to appear within the pyramid's overall design. This raises questions about whether these patterns are purely coincidental or the result of intentional planning. What makes these observations more significant is not any single mathematical match, but the presence of multiple independent correspondences within the same structure. Grok AI identified several distinct dimensional relationships that align with known mathematical constants, each appearing in different parts of the pyramid's overall geometry. These are not isolated instances, but repeated patterns that seem to emerge across different measurements. Individually, each of these relationships could potentially be explained as coincidence or the result of flexible interpretation of ancient units of measurement. Large-scale structures can sometimes produce ratios that loosely resemble known constants when analyzed from certain perspectives. However, when multiple unrelated ratios within the same structure consistently converge toward the same mathematical principles, the likelihood of random occurrence becomes significantly more difficult to assume without further scrutiny. Even more intriguing is the proposed relationship between the pyramid's dimensions and the Earth itself. When scaled using a specific conversion factor, certain measurements appear to correspond closely with the Earth's polar radius and equatorial circumference. While interpretations of this relationship vary among researchers, the pattern itself has been noted repeatedly and remains a subject of discussion. This leads to a deeper and more fundamental question. Were these mathematical relationships intentionally encoded into the design of the pyramid as part of its original construction? Or are they the result of modern analytical methods identifying patterns that were never consciously intended by its builders? Beyond geometric design and mathematical relationships, the physical evidence embedded within the stone adds another layer of complexity to the Great Pyramid. The internal chambers, especially those built from granite, show signs of extremely precise cutting, drilling, and surface finishing. These are not just rough shaping marks, but detailed traces that suggest controlled, consistent application of force during construction. Granite is a dense igneous rock made up mainly of quartz, feldspar, and mica. Its high quartz content places it near the top of the Mohs scale of hardness, making it highly resistant to cutting and abrasion. In contrast, the copper tools commonly associated with ancient Egyptian construction rank far lower on the same scale. Copper is relatively soft and wears down quickly when used against harder stone, raising a basic physical limitation. Shaping granite with copper tools alone would be extremely difficult without additional methods such as strong abrasives or unknown enhancements. Experimental archaeology has attempted to recreate these ancient techniques using copper chisels, stone hammers, and abrasive sand. These methods can successfully shape limestone blocks, but when applied to granite, the results consistently fail to match the precision seen in the pyramid. The surfaces become uneven, cutting efficiency drops, and maintaining consistent depth becomes increasingly difficult. A key piece of evidence is a cylindrical core sample with a continuous spiral groove, indicating a steady rotational drilling motion. The uniform spacing and depth of the groove suggest a level of mechanical control that is difficult to achieve through purely manual methods. When compared with modern machining techniques, these tool marks resemble those produced by advanced rotary or mechanically stabilized drilling systems. However, no direct archaeological evidence confirms the existence of such technology in ancient Egypt. This leads to a clear contradiction. Either unknown methods were used to achieve these results, or current understanding of ancient tool capabilities is incomplete. System-wide analysis and pattern convergence. The key shift introduced by Grok AI is not the discovery of entirely new archaeological evidence, but rather the way it organizes and interprets existing data. Instead of treating engineering, mathematics, geology, and material science as separate and independent fields of study, it evaluates them within a single unified analytical framework. This change in approach is important because it allows patterns to be seen across disciplines that are usually examined in isolation. isolation. When each anomaly is considered on its own, it can often be explained or debated within its specific field. Structural precision is discussed in terms of construction methods. Mathematical patterns are interpreted through measurement systems and possible coincidence. Tool marks and material limitations are evaluated through experimental archaeology. For decades, these discussions have remained largely separate, with each field providing its own localized explanation. However, when these observations are analyzed together as parts of a single system, a more complex picture begins to emerge. The precision of the structure, the consistency of mathematical relationships, and the physical evidence of material processing all appear to align in a way that suggests a higher level of coordination than previously assumed. This does not immediately contradict the conventional model, but it does introduce a challenge. The combined complexity is difficult to fully explain through a gradual, step-by-step development process alone. For the traditional explanation to remain completely sufficient, several highly specific conditions would need to be true simultaneously. The builders would have had to achieve extremely high levels of geometric precision using relatively simple tools. They would have needed to incorporate advanced mathematical relationships into the design without a formal theoretical framework for such constants. At the same time, they would have needed to shape and process extremely hard stone materials using softer metals, all while maintaining consistent accuracy across the entire structure. Individually, each of these points is open to interpretation and debate within academic discourse. However, when combined into a single system of requirements, they become increasingly difficult to reconcile as a purely incremental progression of known ancient techniques. Grok AI does not directly name a single confirmed builder in the traditional sense. However, its system-wide analysis consistently reduces the likelihood that the Great Pyramid was constructed solely through the limited toolkit and methods typically attributed to dynastic Egypt. Instead, the convergence of precision engineering, mathematical structuring, and material anomalies suggests that the commonly accepted explanation may not represent the full origin of the knowledge behind its construction. Human technological development, in most well-documented cases, follows a gradual and traceable progression. Innovations in tools, materials, and construction methods typically emerge incrementally over time. This pattern can be observed across multiple areas of early human development, including pottery production, agricultural techniques, metallurgy, and the evolution of writing systems. In each of these fields, archaeologists can identify transitional stages that show steady improvement, experimentation, and refinement. However, when focusing specifically on the construction history of monumental stone architecture in ancient Egypt, this gradual progression becomes less clearly defined. Early structures, such as the step pyramid at Saqqara, represent significant architectural milestones and demonstrate increasing complexity in design and construction techniques. These developments are widely recognized as important steps in the evolution of ancient Egyptian engineering. Yet, the transition from these early pyramidal forms to the precise engineering of the Great Pyramid at Giza appears, in relative terms, unusually rapid. The level of geometric accuracy, structural consistency, and large-scale coordination observed at Giza does not seem to be fully preceded by a clearly documented series of intermediate constructions that gradually approach the same level of sophistication. Archaeological evidence does not provide a continuous sequence of experimental large-scale structures that clearly bridge this gap. Instead, the record appears to show a comparatively swift emergence of highly refined construction capability, with limited surviving examples that demonstrate a step-by-step progression toward the final level of precision. Geological studies of the Sphinx introduce an additional dimension to this discussion. Certain erosion patterns observed on its surface have been interpreted by some researchers as consistent with prolonged exposure to significant rainfall. If accurate, this would suggest environmental conditions that existed in North Africa during a much earlier climatic period than the generally accepted time frame for dynastic Egyptian construction activities. While this interpretation interpretation remains scientifically debated and is not universally accepted, it highlights a broader issue within the overall discussion. Not all physical evidence aligns seamlessly with the established chronological framework. Different data sets can lead to different interpretations depending on the assumptions applied. As a result, a noticeable gap emerges, not necessarily in the existence of knowledge itself, but in the continuity of its documented development. The progression from early construction techniques to the highly advanced architectural precision seen at Giza is not fully preserved in a clear, linear sequence, leaving aspects of that transition open to continued investigation and interpretation. A boundary in understanding. What Grok AI ultimately highlights is not a single definitive answer, but the existence of a boundary, one that separates what can be confidently explained from what remains unresolved within the current understanding of the Great Pyramid. This boundary does not necessarily invalidate existing research, but it does emphasize that the full picture may not yet be complete. On one side of this boundary are the well-established and widely accepted facts supported by archaeological evidence. These include signs of organized labor, such as worker settlements near the Giza Plateau, documented quarrying activity showing large-scale stone extraction, and administrative records that suggest a structured system for managing manpower and resources. Together, these elements form the foundation of the conventional explanation, which describes the pyramid as a product of dynastic Egyptian engineering, planning, and labor coordination. On the other side of the boundary are a series of measurable observations that are more difficult to categorize within that same framework. These include extreme geometric precision that exceeds typical expectations for pre-industrial construction, embedded mathematical relationships that appear repeatedly within the structure, and toolmark evidence that does not always align cleanly with known material limitations. In addition, some geological interpretations introduce timelines that appear to conflict with the established historical narrative, further complicating the overall picture. While Grok AI does not explicitly declare an alternative civilization or unknown group as the builders, the pattern of inconsistencies it identifies raises a critical implication. The conventional model may describe the process, but not necessarily the source of the knowledge used to execute it. The central question, therefore, is not simply whether one interpretation is correct and the other is wrong. Instead, it becomes a question of whether all of these observations can be fully reconciled within a single, unified explanatory model of how the pyramid was built. Grok AI does not claim to identify the definitive builders of the Great Pyramid. Instead, its analysis points to something more subtle but significant: the possibility that the current explanation, while largely supported by evidence, may not fully account for every measurable aspect of the structure. Whether this gap in understanding points to lost technological knowledge, an earlier undocumented phase of human development, or limitations in how the data has been interpreted remains an open question. What is clear, however, is that the discussion is not fully closed. Grok AI does not issue a direct historical rewrite or officially name a hidden civilization. However, its analysis converges on something more unsettling for researchers. The traditional explanation, while still widely accepted, may not fully account for all measurable aspects of the Great Pyramid's construction. This does not mean the established narrative is entirely incorrect, but it does suggest that it may be incomplete in ways that have not yet been fully resolved within mainstream interpretation. And in that gap between explanation and evidence lies the reason why this discovery has drawn so much attention. Because even after centuries of study, the question of who truly designed the Great Pyramid remains open to reinterpretation. If you enjoyed this breakdown, make sure to like the video, leave a comment, and subscribe for more deep dives into ancient mysteries, AI, discoveries, and unexplained historical phenomena.